So due to the prevalence of ChatGPT, we have a new format for the midterm. Consists of 3 parts based on a topic of interest in the course, and in this particular case for this midterm, we're looking at network pruning, which is the fact, or what we want to do is, what does it mean to do network pruning? Okay, okay. And how do we know if they're important or not? That's a whole point, research question for network pruning. At the end, we could say that we want to take out, we want to reduce the size of the network. So we want to take out some information so that we can run that network on low-powered hardware, right? And that would be edge AI devices, a Jetson Nano kind of device, for example, would be pretty good. But even low-powered MCUs like the Raspberry Pi Pico 2, for example, we want to be able to run inference on that one as well. And the pruning, what we want is the network should be much smaller, right? We want to reduce the size of the network, and at the same time we want to maintain the accuracy, the performance of the network. So that's network pruning. Now in theory we could try all possible things, remove any of, choose n of m weights to reduce or remove, and then check the accuracy, but then computationally that would be much too expensive. So we need to come up with some faster ideas. So that's the topic that we're interested in here. So in order to also give you an idea of graduate school, if you're interested in doing a master's, or to give you some more experience in reading research papers, I included reading the research literature. So I've selected 3 papers that you should read as part of your research into the topic of network pruning. If you use any other sources, then you need to say in your report, in your submission. Then we want to implement some of the ideas, and you have to submit those by Friday midnight. And that should be an implementation of the card detector network, trying to reduce the size as much as possible. And then there will be an exam asking you about all the topics in the research literature in the 3 papers that we included, as well as the implementation that you have done. Okay, so let me just introduce the 3 papers. I already uploaded them to the I cannot actually upload. I can write the reference, yes. They don't open? Okay, if you already have the paper, then you don't actually need those. That is strange. Yeah, let me do the first paper here. And then look at the archive ones. So this is kind of a cool paper in the sense that it actually introduces the idea of network pruning. Anything interesting that you find looking at this paper? Okay, the title is pretty cool, yes, because it basically frames network pruning as sort of damage to the brain, right? And I guess they were trying to make the connection to biological brains as well. The other thing that I think would stand out to me is Jan LeCun, of course. You may know him. He's probably one of the 3 most famous AI researchers in the world. I don't... He definitely won the Turing Award. He may have won the Nobel Prize Award together with... let me check who won this one. Maybe. Oh, John Hopfield and Jeff Hinton. So Jan LeCun is up there with Jeff Hinton as one of the fathers of modern AI. This is one of the earliest papers. 1989 is extremely early for deep learning research, right? In fact, for a while, I think LeCun was the only one that was seriously pushing neural networks. And also before he actually did the work on MIST, like the numbers recognizing system, which was the first convolutional neural network. So this is very early in research, and it's kind of interesting to see that even at that time people were looking at pruning methods. But it introduces some of the formalisms. And approaches. Okay, then the second one would be paper. And this would be the correct link. So what's wrong with my link? Oh, there is, okay, there's an extra TD there. So they called their approach network slimming. there are the 3 papers. They're all freely available download. You can download them, and I also uploaded them to the Discord already. So right now, you have a network that can detect the different Blender cards, right? The different cards from Blender, like if we use the Blender file to generate the images. And that is a relatively simple problem. The VGG network can classify that with 98% accuracy quite easily, right? So now you want to take your network, whatever you implemented before, which could be the version that I have or something that you generated yourself. To prune the network. And let's say we talk about pruning the network, then I can have a statement saying I want you to make the network smaller so that it's only 10% of the original size, right? But it's not quite clear what that actually means, because am I talking about 10% of the number of neurons that I have in the original network, or 10% of the weights that I have in the original network, or 10% of the multiply and add function calls that I need to make, right? So that also shows that there's different ways in which you can actually consider what you actually want to reduce, right? And That depends a little bit on what the final architecture is that you want to run on. So for example, what would be the representation of your neural network in memory or on your GPU? How is it actually represented? Like what actually sits in memory? We can think of the network as a 2D matrix, right? Where we have n neurons and n neurons here, right? Which is the total number of neurons that we have in our network. And then this would simply be the weight matrix. Right? That would be the most straightforward implementation or representation of the network. And then that would include a whole bunch of floating point numbers. For example, neuron 0 is not connected to itself, so its weight is 0, but it has a weight of -2, -1, 1, 5, 3, 2, 1, 2.2, -1.7, so on and so forth. Right? And if you do that for the entire network, then that's a little bit, if you have a network architecture with like convolutional layers and fully connected layers, then that wouldn't be so efficient to do that for the entire network, because you kind of have blocks. So there would be huge areas of 0 here. So then you could also, if they are large enough, you can have like different sub-blocks of these that you can upload to your GPU. Right? And then what would be pruning the network then? So this corresponds to this would be some network architecture, right? And then the fine-grained pruning, the most fine-grained thing we can do in order to change this network would be of somewhat of the weights, right? That would be the first step. And if I get rid of some weights, what would that mean for my matrix here? No. Okay, it would change the weights to what? Right? Yeah. And would change to what? Huh? let's say here, this is neuron 1, neuron, neuron 2, and this is neuron 5, right? So I have a connection from neuron 2 to neuron 5. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, so on and so forth. So from neuron 2 to neuron 5, I have a connection, and let's say it's minus 0.16, right? That's the current weight. If I want to reduce the weight, if I want to remove that weight from the network, what would I have to do to the matrix? I would have to overwrite this and change it to 0, right? Because 0 means the two neurons are not connected. So this would be the pruning of the weights, and this can be very small changes. It's very fine-grained, like you can make very small changes, very specific changes to the network, right? But the problem with it is that for a large network, if you run it on a GPU, then what you can do is you upload this matrix or this matrix into subblocks, and then you pump it through the GPU. So in that case, this doesn't really help you as far as inference speed is concerned, right? Because your GPU will still multiply, calculate the dot product of two large matrices. It just happens that some of the values in there are 0. So on a GPU, you would not see, on a standard GPU, you would not see a speed up. However, this technique is quite powerful and useful, so the NVIDIA guys are very smart, so now the latest generation of I'm not sure if it's the latest or the previous 2 generations, the NVIDIA GPUs actually have a sparse mode. Because in this case, what you're doing is you basically create sparse matrix there. So they have a sparse mode, and then for certain settings, it won't do all the calculations if some of the weights are 0. So in that case, even your GPU can speed up the computation. Now, if you implement this on a microcontroller, then of course, you can easier get a speed up, because you can check, you can say, oh, that weight is 0, so I skip the entire calculation of the dot product in this case. So then your code on the microcontroller will become a little bit more complicated, but in general you can get good speed ups. You can make use of large blocks of zeros in your matrix. So it depends on what your output system is. If it's a Jetson Nano, which is a popular edge AI computing device, setting one of the weights to 0 won't actually help you with your inference speed. Because if you put it on the GPU, the Nano GPU is not smart enough to be able to take advantage of the zeros in your matrix. It'll just calculate the dot product with 0, but keep adding them up. So 0 times 1 plus 0 times 5 plus 0 times minus 3. It'll go through the whole vector. Right? So that would be one way of pruning. The so what would be better? What would allow us more speed up? Yeah, if we get rid of the whole row, that would work, right? Then my matrix will be smaller, I'll have a good speed up from that. But that is very coarse-grained then, right? Now I have to get rid of all the entries in a particular row and a particular column. The speed up, however, you can gain that then on a microcontroller or on a GPU, a standard GPU, not a fancy sparse GPU. And what would that mean with respect to the network if we get rid of one row? We'll get to that in a second. What happens if I get rid of this row here? We completely disconnect what? The neuron 3, right? So if we completely disconnect the neuron, that means we get rid of the neuron, right? So if you cut a neuron out here, let's say this is neuron 3. If you cut out this neuron, then it's completely gone. But that's a major surgery. Right? That's more coarse-grained surgery. And the papers that I provide you with are giving you some ideas for now there's kind of only two choices, right? Or two things to consider. One, do I prune at a fine-grained level, or do I prune, which means at the level of the weights, or do I prune at the level of the neurons? What's also called the channels, which is a more coarse-grained operation. And the choice there depends on what your output hardware is, what you actually want to run it on. Because if you do fine-grained pruning on a GPU, a standard GPU, you won't actually gain anything. You might as well not bother doing that. And then, let's say we decide to prune based on weights, then what's the question that we need to answer? Which weights, right? And if we want to prune neurons, we have to decide which neurons. And the papers that I present, they basically have different algorithms for how to choose them, because you cannot just try all possible combinations of neurons that you want to reduce. Computationally, that would take way too long, right? So how do you think they choose which neuron to eliminate? Like, how would you pick a weight to remove out of the table? Yeah, the smallest one, right? So you take the absolute value and you pick the ones that are the smallest one. That's a reasonable heuristic, right? And then you can do more than that, in the sense that you say the smallest 10% of the neurons, something like that. Right? Not just a single weight that you want to remove. You want to remove 10% of the neurons. Then you need to sort them, find out the 10% of the neurons, what's the threshold, and then you can delete all of the ones with the threshold, below the threshold. That's one of the methods that is described in the paper. Um, so that works on an individual weight, but how about a whole row? How could I determine whether I want to, which row I want to reduce or remove? Well, we're getting to that in a second. The middle one, which middle one? No. Huh? Where all the weights are zero, right? Correct. So there's different ways to determine how small the vector is, right? The simplest one would be to just take the L2 norm, but there's other norms that are discussed in the research that give you slightly better results. But the idea is to find a row where all the numbers are really small, right? So now you've pruned one row or n rows or something like that. Then what do you need to do?
Retrain.
Then you have to retrain, yes.
But then what does it matter which row you modify? Like you remove.
Okay, you don't start with random weights, right? You would start with the current network architecture that you have with the neurons removed. So you would do fine-tuning, you would not do train from scratch. Correct, yeah, that's the idea, yes, yeah, yeah. If I do retraining from scratch, then it doesn't really matter which, let's say here, it wouldn't matter which one I cut, because basically I'm saying, oh, 4 should be enough, right? Like I have 5 neurons here, and I say, oh, I want to reduce it to 50% of the size. So 3 should be enough. And then I retrain from scratch, then of course the network would learn whatever it would pick. So no, we have the weights. The idea is that it's a reasonably complex task. Right? If you can retrain it in a minute, then yeah, you don't need to worry about pruning, because, but then your network is so tiny that probably cutting it down to a smaller size won't make much difference either. So we're looking at something like 100 megabyte kind of network. Takes a couple of hours to train. You don't want to redo that all the time. So now, there's different ways to do the fine-tuning. One is if I want to reduce 10 nodes, right? Or I want to reduce 100 weights, then one way of doing that is to reduce 100 weights, then do the fine-tuning, right? To get my final network. What works slightly better in practice is to do it iteratively. So, very good, yes, nice. So you cut one row, then you retrain, then you cut the next row, then you retrain, then you cut the next row, then you retrain. That, on average, that's computationally more expensive, you have to do more work, but the fine-tuning usually doesn't take several hours. It's significantly faster than training the original network. So that's the implementation. So when we talk about 10% of the weights, let's make that precise. Actually, we want to have several thresholds. Let's do it like this. 50%, 25%, 10%. Mhm. Eventually, but if you look at the papers, clearly there's a limit, right? Because otherwise I would just prune everything down to 1 neuron, one weight. If I maintain the same accuracy, then every computational problem in the world would be trivial. So clearly that doesn't work. We can even prove that it's not even possible to reduce just one weight and maintain the same accuracy in all cases. Why? It's the same argument that we have for compression. There's a theorem in compression that says it's impossible to implement a compression algorithm that will take any input and reduce it by just 1 bit. Okay, we'll get to that in a second too. Yes. First of all, it's impossible to have a compression algorithm that will take any input file and reduce it by just 1 bit. The reason for that is if such an algorithm occurs, right, I start with a file with 100 megabytes, I compress it, I get rid of 1 bit, right? But now I have a new file. Then I load that into my algorithm again. Now it will be down by 2 bits. Then I load it again, 3 bits, 4 bits. So if I do this repeatedly, I would be able to take any file and compress it down to a single bit, which clearly is not possible. And the same thing with the network. There's no way that you can develop an algorithm that will be able to remove a single weight from every network that you have, because if you could do that, you would remove the first weight, the second weight, the third weight. Eventually you'd be just with a network with 1 neuron, 1 weight. So clearly that doesn't work. But the compression ratios that you can achieve are pretty spectacular. Like they are not trivial. So here they go from 138 million to 10 million. So that's down to 10%. So that's a 90% reduction of the original network with no loss of accuracy. They reduced it by a factor of 9 times from 61 million to 6 million for AlexNet. So that is quite significant reductions in the networks that we can do. I guess because people are just dumping them on GPUs, nobody really was interested in like optimizing the network architectures. And also, so far, we talked about the weights and the neurons, right? The channels that we can reduce. And we said that for that, the weights would be important, right? Because low weights would mean that the neuron is not very important, so we would think we can cut it out. However, that is not entirely true, right? Because what determines the importance of a neuron? It's not just the weight, but it's the entire activation of the neuron, right? It's the weight multiplied by the input. If your input is 0, then your weight could be minus infinity plus 1 million, wouldn't make any difference, right? So in fact, some of the more sophisticated approaches to pruning use the activation rather than just the weights. But how do we get the activation? Yeah. So that means you need to have some kind of sample data set that you can use, and you can run that through the network, and then you look at what the activations of the individual neurons are. And if you do that, you can reduce the neurons with the smallest activation rather than the smallest weight. That usually results in better performance, but you need to have some kind of sample data set. Right? But that works. So there's kind of weights, activations, and neurons that we can prune. And if you look at the TensorFlow Lite converter, when you run that in order to bring it on your Android phone, if you look at the actual documentation, there's a way that you can run it with some sample data, and it does the quantization for you, and it uses then your sample data in order to do pruning based on, because TensorFlow Lite can prune a network for you too and do a quantization of the network. Where quantization is, yeah, so floating point 32 to floating point 16 to integer to int8 to some of the more recent large language models are actually quite interesting because they changed their activations to be just -1, 0, and 1. So they're called 1.58-bit encoders, because you have 3 states, and if you calculate the entropy of 3 states, the minimum number of bits it takes you to encode a message with 3 possible states, it's the log 2 of 3, which is 1.58. So that's where if you see some kind of LLM with 158 in it, that means that they quantized the activations to be just one of 3 states, +1, -1, and 0. So kind of like a ternary logic. So in this midterm, we don't consider quantization. We'll do that later on in the course. So this is only about pruning. So you don't need to convert from floating point to anything else. But TensorFlow Lite does that, because TensorFlow Lite can only deal with integer weights and integer activations. So here we don't include activations. We just do weights and neurons, which basically means it should work on any kind of input data. Okay. And what you want to start out with before you do the pruning, after you implement it, some of the visualizations are quite nice and make it clear what's actually going on. So the first one is you want to show a histogram of the weights before and after pruning. So this would be the value, the weight, and this would be, you want to show a histogram. So on the x-axis you would have the weights, let's say this is 0, minus 100, 100 for example, whatever the maximum range of your weights are in your network, and then you want to show what that looks like. And then after pruning. And the same thing for the channels, the neurons. And in this case, the weight would be the length of that vector, however you define, whether you use Frobenius norm or L2 norm or what. No, you should compare the performance of both of them. Yeah. But before you do any pruning, you show the histogram to give you an idea of what the weights look like. And then you need to show the sensitivity plots. Then implement algorithms for selecting weights and channels to be pruned. Okay, so two algorithms, one to select the weight to prune, but you do that by looking at the sensitivity plots usually. Right? And then compare the performance of weight and channel pruning to see what the accuracy that you can achieve and the reduction you can achieve with both of those. Yes, so right now we do the pruning, we assume that we use a microcontroller. So we will get a benefit in the end. So on an Android phone, if you just run the straight TensorFlow library, then I think it only uses the CPU, in which case your pruning the weights will still have a benefit. If you use the OpenCL Intel extensions for vector GPU processing, and you can turn those on in TensorFlow. Oh, actually it's not TensorFlow, it's the LightRL now. LightRT now. It's called LightRT. It used to be called TensorFlow. There's a way that you can enable the OpenCL extensions, And then it will use it like a standard GPU, in which case you won't get any benefit from um, fine-grained pruning. But we ignore that for this. So you can run the whole thing. You don't need to run this on the Android phone. You can just run it on your laptop.
So it will work.
Hmm?
So it will run it in Google Colab.
It will work, yes.
It will work.
Yeah, yeah. Mm-hmm. Yeah. So we're looking more for a theoretical speed up here rather than the actual speed up on a Zenfone 6 running this version of the operating system with these settings. Okay. Okay, good. Then so I think the best way to do it is to actually use GitHub repository for you to submit your work, your submission. So create a private GitHub repository. Include all your code. Include your graphs. Include graphs. Histograms of your research. And then write a 3 to 5 page report. And include the honesty declaration, which includes all the external sources that you used in your implementation. So I uploaded it to SLM. You can just download it, fill it out. So you can use ChatGPT, but you need to tell me what prompts you used. And I caution you against just blindly copying and pasting the output of ChatGPT, because in the oral exam I'll definitely ask you about your code, ask you to make changes about the program that you wrote and the research that you read. And make sure you keep that GitHub repo private until Saturday, after the deadline. Okay. So that will be the oral exam then. So I think it is a good format. It's much more work than what I used to do, but for me it's much more work than I used to do. For you guys it won't actually change that much, apart from the oral exam section. But the oral exam, I hope to be able to do it with just 10 to 15 minutes per student. Okay? Any other questions? Correct, yeah. Correct, yeah. That's the plan. Yes.
But we need to complete it before to this.
No, you just need the network. And I already gave you the code for the network. If you, the card recognizer thing already has the code to do the training using Blender. So you can start.
We can modify this code that you.
You could modify this code, yes. You can of course also use your own network architecture. If you have already done more work on assignment 3 and you have designed your own network architecture that you're happy with, then you can use that as well and try and prune it. Correct, yes, yeah. And it will be kind of interesting to see how much we can actually prune on these particular networks. Right? Good. Also, I think the format is a good opportunity because if you are doing a master's, and definitely if you do a PhD, even more so, then the kind of reading research papers, doing some implementation, writing a report and answering questions about it is basically what you do all the time as a master student, right? Or what you should be doing all the time as a master student. All the time that you're working on your project. Of course, you also have free time and stuff. Anything else? You guys? Ray? Kevin? What? The paper, not yet, no. I'll, yeah, yeah. No. Those are implemented in Torch. You don't implement the convolutional network from scratch. You implement pruning of the network. Pruning. Read the 3 papers, it should tell you what you have to implement. Your network should detect the cards from the Blender image, just the synthetic images from Blender. Doesn't need to be real world images. No, it's a Blender file. You can run it, you get 100 PNG files. You get hundreds of images. In the Discord channel. Yeah, cards.blend. No. No, were you like asleep in the last month or what? This is a Blender file with a Python script. If you run it, it generates a whole bunch of images, assuming that you have the cards. You need those cards here as well. And then you get something like this. Correct. And then you try and make the model smaller. Smaller. So that it runs faster on the phone. Like just goes on and on. If you want more, you can generate more. Correct, yes. Cards, and also the orientation of the card. Pitch you. It's on the table, so there's only one angle that you can rotate. And it's encoded in the file name. Like if you look at the files, this is a 2 of clubs at 169.78 degrees. You can just read the Python code. Just read the Python code in the Blender file, you'll see what those numbers mean. Okay, any questions from Jay or Justin? They're online. Okay, good. Then yeah, that's it for the midterm. Oh, sorry, wrong. This one, yes. I'll just update the link. Okay, so let me check. Yeah, so this is a midterm one now. Yeah. And yes, you can use the card recognizer to start. Okay, good. Then what's the status for the third assignment? You finished? Haven't started yet. Okay, then you'll have a busy week ahead of you. And you will have to take some real images. Yeah. Mm-hmm. Yeah. That's not surprising if you have no card images in the thing. And David, you finish your recognizer? Card detector? Okay, but what's the video that you posted? Oh, spades 4, 92%. Queen, spades 9, something 8. It seems to work okay. Yeah, yeah. Yeah, okay, good. You, assignment 3? Not started yet? You? No, okay. You'll have a very busy week ahead of you then. Actually, I did do the trick, the magic trick at the Robotics and Education conference. And they thought it was cool.
You did it yourself or with a robot?
I did it myself. Yeah. Actually, the other thing we need to check is with your bicycle cards. With your bicycle cards, we need to check if they actually look the same, because some of them are different, right? Yeah. Yeah. The jack, yeah. Mm-hmm. Yeah. Luckily, we don't need to detect the jack because it's not, it's invariant to rotation, so we won't be using it. Right? Like we'll only use 7 and 9 and 2, some of those cards. Ace. So then if you take images of the real cards, then it would be nice if you could share them with the other students, so then not everybody has to take pictures. Yeah. Okay. What card? The Blender file is in the Discord channel. I posted this already. Cards.blend, 2 version. Why? No? You can just run those. It's like the other cards is like a gigabyte already on this computer here. Yeah. Yeah, yeah. Yeah, it just takes a couple of minutes and you have hundreds of cards images. And I can't upload like half a gigabyte to Discord. No, you do your own Blender thing. Assignment 3. It's already, I posted it somewhere, right? Detect the cards using the Android phone. Yeah. No, you have the video camera running on the phone because that'll be your robot, right? What? Then borrow one from David or somebody. Or run it on the emulator. You can run it on the emulator. Yeah. Monday. No, Monday next week. Have you been like kidnapped or something? No OpenCV. No OpenCV. We use a neural network to do the detection. Actually, Kevin, whatever your professor knows, probably not that much. I'm sure if you ask ChatGPT, everything will be fine. Yeah, now you have a little bit of a problem, don't you? Okay, also since I have you here, okay, so I stopped recording. I don't think